In our last class, we established the fact that every conductor embedded on them, they have electrons. But those electrons are static. They are static. In order for them to move, we have to create a PD using a battery or electric cell to create what we call electromotive force to drive the electron around, or to drive the electrons between the terminals of the conductor. And that is what we call electric current. Before they can be current, they must be source of PD. And we look into Ohm's law last class, and we show that potential difference equals to the current times resistance. So one of the sources of EMF are electric cells. We have other sources. So electric cells, they are from chemical energy. So these electric cells are chemical cells. So they are gotten by converting chemical energy to electrical energy. In our next class, we are going to deal with that. So we are going to talk about types of cells and the like. So the electric cells, their PD, when they are not supplying any current, is called EMF. So what is EMF? EMF is the potential difference across the terminals of the cell when it is supplying no current. Please, you have to know this. If we have a cell in a circuit, for example, let's consider a circuit. So this cell has EMF of what? E. Suppose the EMF is 9 volts. So this is all called open circuit. When the circuit is open, no current will move across the circuit. So the PD across the terminal of this cell, when it is supplying no current, is all called EMF. So EMF is the potential difference across the terminals of the cell. You can write that, please. Potential difference, sorry, EMF is the potential difference across the terminals of the cell when it is supplying no current or in an open circuit. The potential difference across the terminals of the cell when it is not driving any current or when it is in an open circuit. Now, what happens in a closed circuit? If we press this switch down and the circuit is closed, what happens? Current will start flowing. Now, as soon as this key is closed, this is all called a closed circuit. When the circuit is closed, current will be driven around the circuit from the negative terminal to the positive terminal. So there will be a current, and this current will move around in a cycle, keeps going. So this external resistor or load will receive this current I. But there is a small problem here. When the current goes, when it is returning, it has to pass through the battery itself, through the cell itself. The cell itself is a conductor, and every conductor must resist flow of current. So this cell also have its own internal resistance. Sometimes you'll be told to neglect. If you are told to neglect the internal resistance, it means the EMF equals to the current times R, the external what? Resistor. If we have more than one resistor, we use total what? Resistance, effective resistance. So this one is, if you are told to neglect the internal resistance, this R represents the internal resistance of the cell. But some cases, you will not be told to neglect it. So now let's draw a cell showing the internal resistance, its internal resistance. Now in this diagram, this cell has an internal resistance small r. Then what happens? It will drive current will flow because the circuit is closed. The current I will flow. So this I will flow and pass across what? This R. So the current across this is R. Now, note this. When this current is coming back, there will be a voltage drop across this resistor. And when it's coming, there will also be a voltage drop across the internal resistance of the cell itself. So it's as though we have two resistors in series. They are not in series because the current that passes through this R is all passed through this R also. So, obviously, for this resistor, this external resistor, it will take a voltage of this total. Recall in our last class, we did what we call voltage divider rule for two resistors in series. So it means the voltage that will supply to this load, let me call it VT, we call it terminal voltage, or terminal voltage, VT, equals to, according to what I did yesterday, that will be R over R plus R times E. So this is the voltage that will supply to the external circuit. And for this small r, it's also going to receive a voltage. We call it VL, we call it loss voltage. Loss voltage, and that will be following the voltage divider rule, small r over R plus R times E. So if we add this voltage and this voltage, we'll get the total EMF. Total EMF equals to what? VT plus VL. And if you have to apply Ohm's law, for VT, the voltage across the resistor is going to be IR. that will be I, then R. For this small r, its own voltage will also be IR, I and small r. So from here, it means E equals to I into R plus small r. So this is the internal, sorry, this is the PD, potential difference. Now recall what we did here. If our R is 0, if this battery has no internal resistance, or if we neglect its internal resistance, R becomes 0. If we set this R to become 0, what happens? We are having E equals to IR. Because 0 plus R is 0. So following this. So this our E will now be what? The terminal voltage, the voltage supplied. So we can call this E our V. V is equals to IR. So meaning, what we did yesterday, or in our last class, still holds if the cell has no internal resistance. It always have, but if the internal resistance of the cell is neglected. If it is not neglected, we have to consider this. So new for a cell now, the EMF equals to the current supplied, R plus small r. R is the resistance of the load supplied to the external circuit, while R is the internal resistance of the cell. And this is voltage drop outside, supplied to the external circuit. This is the loss voltage. To understand this better, you will understand it better with an example. Let's give an example. For example, let's consider this single circuit. This voltage, this battery has EMF, this 12 volts. We are not going to call it V again. We'll call it E. So it means the EMF of the cell is 12 volts. And normally this 12 volts is what is meant to be supplied to these 5 ohms. So the volt that will be what? 12 ohms. But the volt that will be supplied to this one will not be able to 12 again. Why? Because because of the internal resistance of this cell, there will be loss voltage. So instead of 12 to supply to this one, the voltage that will supply to these 5 ohms now is this. Is our VT, which equals to R, what's R here? 5 over R plus small r. That small r is 1. 5 plus 1 times E. What's our E? 12. So 5 plus 1 is 6. 6 to 12 is 2. 2 times 5 is 10. So the terminal voltage is 10 volts. So from 12, if 10 is for the terminal, then the loss voltage was 2 ohms. We do 12 minus 10. But let's still use this formula. So what was VL? Loss voltage. And that was what? Small r. What small r? 1 over big R, 5 plus 1 times E, 12. 5 plus 1, 6. 6 to 12, 2. 2 times 1, 2. So it means the loss voltage equals to what? 2 volts. So what happens now? It means, okay, let me rewrite this one. Now, so if this cell has no internal resistance, the PD across these 5 ohms is going to be 12. But now it's not 12 again, it's now 10 volts instead of 12. 2 volts is loss. So we call this one voltage, loss voltage. And this one is called terminal voltage, loss voltage. If we add a terminal voltage plus low voltage, you get the EMF. That one is telling us. The EMF E, 12, equals to VT plus VL. 10 plus 2, 12. This is it. So E equals to VT plus VL. That's how this one comes to be. And what is terminal voltage itself? According to Ohm's law. From Ohm's law, let me write it here. From Ohm's law, VT, let me just write here. The terminal voltage is IR. And the loss voltage is also IR. But in this case, internal resistance, this is what? The external resistance or resistance of the load. So suppose I give you the question. A battery of internal resistance 1 ohms and EMF 12 volts is connected across a 5 ohm resistance. What is the voltage supplied to the 5 ohm resistance? Or is it 10 volts? So just draw a circuit. But if you are told, neglect the internal resistance. If you are told neglect the resistance, come here. So it means our E straight equals to what? IR straight. Then what will be supplied to this one is just IR. So we need to get I first. Since you are not given I in this question. And how do you get I? Oh no, we don't need to do that, because if there is no internal resistance, all the 12 volts will be for this. Now for this particular one, let's now calculate the current. Let's calculate the current in this case. So How can we get the current? We can get from this formula. In fact, from that formula, we can write out the current. So from here, it implies that the current equals to, divided by R plus R, that's E over what? R plus R. That will be the current that will be supplied. Formula for current from there. So now let's now get the value of current from this question. So the current I becomes, what is E? 12. R plus R, that's 5 plus 1. So the current I equals to 12 over 6. Current I in this case equals to what? 2 amperes. If you don't use this formula, to get the terminal voltage and loss voltage, we can use this formula to get I first. After getting I, multiply this 5 by 2, you get this V, 10. Multiply this 1 by 2, that's you get what? Vm, 2 volts. So this is for a single cell. A single cell. That's all you have to know. But one external question or even jam, in a way they can coin it. Differentiate between EMF and voltage. This VT is voltage, it's not one EMF. This EMF. This EMF, this voltage. This is also voltage. This one is lost, this one is useful. So this one is what? EMF. So EMF is the potential difference, we've done that before, we've seen that before, across the terminal of a cell when it is supplying no current. When it's not supplying current, we don't call it EMF again, we call it what? Voltage. In this case, they are still equal because we didn't include the internal resistance. But now, let's not come here. This diagram is not realistic in real life. This one is realistic. So this time around, if you are to calculate the PD across the terminals of this cell now, is going to be less than 12 volt, like in this case. In this case, if you have to measure the PD across the terminals of this cell, maybe from here to here, it will not show you 12, it will show you 10. If it has no internal resistance, it will show you 12. But because of the internal resistance, the loss voltage, it will show you 10. Even at this, if it has internal resistance and you open the circuit, if the circuit is open and you measure the voltage across it, you will still get 12. But once the circuit is closed, for this case, if you measure the PD across its ends, you get 10. 2 has been lost due to the internal resistance. So what is voltage? Voltage is the opposite. Voltage is the PD, potential difference, across the terminals of a cell when the circuit is closed. Or voltage is the potential difference across the terminals of the cell when it is supplying current. This one, when it does not supply current. So E, V, EMF, voltage, they are both what? PD. So EMF is the potential difference across the terminals of the cell when the circuit is open or when it is supplying no current. Voltage is the potential difference across the terminals of the cell when the circuit is closed or when it is what? Supplying current. So you have to know that it's very, very important. You have to know. So ordinarily this ought to be the end, but you have to also know something. It is possible to connect two cells together to form a battery. In this case, we have a single cell. What if you have more than one cell? Yes, we can have more than a cell, and it can also be connected either in series or in parallel. So now let's move to cells in series. Cells in series. Now, suppose this cell has EMF E1, EMF E2, EMF E3, internal resistance R1, R2, R3. To connect this cell in series, we are going to combine the positive terminal of the first to the negative of the other. The positive of this to the negative of this, and this positive to this negative. So if you connect them this way, the EMF will add up, and we are going to get something like this. Now in this case, the effective EMF, let's write E equals to E1 plus E2 plus E3. If they are more than that, you keep adding until you get to the last cell. Then all their internal resistance is also in series. So total internal resistance R becomes what? R1 plus R2 plus R3. And this formula still goes. Their E equals to I into what? R plus R. So this E now becomes total EMF. This R is total what? Internal resistance. While R is what? Total external what? Resistance. That is for cells in series. But note this configuration: long to short, like that. If the terminal of one of them is swapped, let's swap this one. Instead of short long, let's make long short and see what will happen. Just note, if you swap the terminals, the EMF becomes negative. Now look at this. This one is positive, negative, positive. So if this alignment is correct, minus plus, but this one is plus minus. If you swap the terminals, it becomes negative. So in this case, total EMF becomes what? E1 minus E2 plus E3. And that is why if you have two cells of equal EMF and they're connected this way, this is E1 and this is E2. If E1 is, let's say, E and E2 is also E, in this case the effective EMF equals to E1. This one that is swapped will be what? Minus E2. E1 is E, E2 is E, E minus E 0. So if you have two identical cells or battery and you arrange it this way, the bulb is not going to turn on. For example, the popular battery that we used to use here in Nigeria, so we have something like this. So when we want to connect the batteries, it must be connected this way. In this way, the effect add up. So let's suppose you have a wire here, and I connect it to a bulb. Let this be a bulb. So when you close the circuit, what happens? The bulb will lit. So let's suppose this one is 1.5 volts, and it's also 1.5 volts. So total voltage supplying current to this is going to be what? 1.5 plus 1.5, that's 3 volts. But if you connect them this way, what will happen? Even with the key closed, this thing will not light up. Why? The first one is 1.5, the other is 1.5, but instead of adding, like in this case, that it add up, one of them has to be minus. Why? If you take this one to be positive, minus plus is positive, then this has to be negative. So by the time you combine it, 1.5 minus 1.5, that will be 0. So when you're connecting battery, you have to follow this or this. But if you do it this way, the bulb is not going to light, meaning the voltage will cancel each other. Now let's talk about cells in parallel. For cells to be parallel, similar to parallel resistance, so the end of each have to be connected. This end with this, this end with this, We can arrange them vertically this way. But note, when cells are arranged in parallel, most times they used to have the same PD. They have the same EMF rather. For parallel arrangements, all these terminals will be joined. All this will be joined. Sometimes they can put a point here and join everything here this way. Same thing. So let's call this one E. Let's call this one E1, E2, E3. Suppose they have same internal resistance R. So when cells are in parallel, the effective PD equals to what? E1 equals to E2 equals to E3. So when cells are in parallel, the effective PD is what? Or the effective EMF is the EMF of one of them. Suppose this one is 1.5, 1.5, 1.5. Total EMF is just 1.5. So that will be total EMF. Then what will be the total internal resistance? Now here we are having three resistors in parallel. Recall, for resistors in parallel, the effective resistance is what? The reciprocal of the sum of the reciprocal of the resistance of which resistor. That's the formula for cells in parallel, which we've done in our last class. Here we have what? 1 over R 3 times. That's what? 3 into 1 over R. You can write as 1/3/R. And from here, it means total internal resistance becomes what? R/3. Now, if you have just 2 cells, it will be R/2. 3 cells, R/3. If you have n cells, the effective internal resistance RT becomes R/n. So it means the more cells you have, this inverse variation, the effective internal resistance is inverse proportional to the number of cells. So what is it telling us? It means if you have plenty cells in parallel, if n is very big, RT will be very small. So it means the effective internal resistance will approach 0. It gets smaller, smaller, smaller. And when a cell have very low or negligible internal resistance, then the efficiency will be very high. Why? If the EMF is 12 volts, it's going to supply almost 12 volts if R is nearly 0. So meaning the advantage of cells being arranged in parallel is that the effective internal resistance will reduce, hence the efficiency will increase. What's the efficiency of a cell? A cell that is built to give out 12 volts, like the example we did, is now giving out 10 volts because 2 volts is lost. So how do we calculate the efficiency? The efficiency is output to what? Original. So this is what is meant to give out, this is what is giving out. So out of 12, it's giving out 10. So you can say the efficiency of the cell in percentage equals to what it is supplying over what it's meant to supply times 100%. That's the efficiency of the cell. And what is VT? From Ohm's law, VT is just IR. What is big E? We've done that before. That's what? I into what? R plus R. In this case, I cancel I. So we can say the efficiency of the cell equals to R over R plus R times what? 100%. If you have more than one cell, then use what? R total here. Then according to what we have here, the more the number of battery we have, the lesser the what? RT. So the efficiency and the internal resistance, they are what? Inverse proportional. If this R is constant for a particular circuit, the smaller the internal resistance, the more the efficiency of the battery. So cells connected in what? In parallel will last longer because the loss will be what? Minimal. So in case you are asked, for a cell to have to increase the efficiency of cells, they are meant to connected in dash. Is it series or parallel? The answer is in parallel. Because in series it adds up. So what is R? Let's suppose this R is 1 ohms. So it means at the end of the day, I'll be having 1/3. That will 0.33 ohms. That will be effective. In this case, I'll get 0.33 ohms. But if it has been connected in series, that will be 1 plus 1 plus 1. That will be what? The effective in that case is going to be what? 3 ohms. 3 ohms, 0.33. This is extremely smaller than this. Although when cells are connected in parallel in series, their voltage increases, but they have lower efficiency. Note this point about cells in series and cells in parallel. This will be the end of electric field 2 part A. So let's also solve more questions. So far we've talked about current, voltage, resistance, factors affecting resistance of resistor, resistivity, electrical energy, that was buying and selling, electrical power, and now we've also talked about Ohm's law, and now electric cells. So in our next class, we are going to talk more about conduction through liquids. So how does electric cells work? And we're also going to talk about electrolysis and also conduction through gases. But for this class, what is meant is to solve questions. The first question we're solving is from UTME 978 number 27. 3 5-ohm resistors are connected in parallel. So this is parallel arrangement. What next? Have a potential difference of 60 volts. So within these two nodes, the potential difference is 60 volts. What's the question? The current in each resistor is, we want to get the current in each resistor. This is extremely simple. Why? We are going to use Ohm's law straight. There is nothing about internal resistance here. So if there's no internal resistance, the limit mentioned it, we also use IR. Now they are in parallel. They're parallel, it means they have the same PD. The PD applies is 60, 60, 60. And from here, I equals to V over R. So for this first one, the current equals to, what is V? 60 over R, 5. And the current here is what? 12 amperes. Since they are all 5, 5, 5, it means the current in each is what? 12, 12, 12. As simple as that. So this actually means that the total current driven out is going to be 36. 36 will come out from here. 12 will enter here, 12 enter here, 12 enter here. They all connect back as 36. To be sure it will be 36. If you combine these 5 in parallel and get the effective resistance, then divide by what? This 60, using because of IR, 60 over the effective resistance will get 36. And it's going to be shared equally. Because normally, if they are in parallel, it's meant to be different current that will flow through them. But because they have equal resistance, the current will be the same. Let's put another question. Now, listen to the question. 979.12. This one is more complex. The question says, in the given circuit, in the figure, cell P has internal resistance, has an EMF of 1.5 and internal resistance R. Then cell Q has an EMF of 2 volts and internal resistance of 1 ohms. If the ammeter reads, this ammeter reads 550 milliamperes, then R is equals to, we want to get the value of R here. If you're not careful, most people miss this question. First, they mention internal resistance, so we're not just going to use because of IR. Now, for this first one, we have 2 cells. We have to get the effective what? EMF. I told you, if you have only 1 cell, you have to get the effective. So what will be effective? Now, check this one. Positive, negative. It's meant to be positive, negative, but they do negative, positive. They swap the terminal. So the effective EMF is actually going to be what? 2 minus 1.5. 2 minus 1.5. And effective equals to what? 0.5 volts. Most students will hurdle because they won't see this. You have to be very careful. Now we know the total EMF. What is the formula? Total EMF E equals to what? R into what? R plus R. So this R is the external resistance, which is going to be 7. Our E 0.5. Our I 50 milliamperes. 50 milli actually means 10 to the power minus 3. Because current is ampere, there is no milli normally. So this milli you have to replace with 10 to the power minus 3 into what? 7 plus R. This R now is not the effective what? Internal resistance of the 2 cells. Then from here, we have 0.5 equals to 0.5, 7 plus R total. R is 0.5. This actually means over 1000. So sorry, 0.05. 0.05. 0.05. So we can divide both sides by 0.05. 0.05 over 0.05. This will give us 10 equals to 7 plus RT. Then RT is what? 10 minus 7, that is 3 ohms. So it means if you have to add these two together because they are in series. So RT from what you have here, RT is actually 1 plus R. That's R plus 1. And what's RT from here? 3. So it means R plus 1 is 3 ohms. R is 3 minus 1. Then R is what? 2 ohms. So it means the internal resistance of this cell is what? 2 ohms. While this one is 1 ohm. Can you see? First, the terminals, and I explained in the lecture. Second, this formula. If you have only 1 cell, you have to look for the effective, which you're looking for here, which you look for here. Then RT, we've got a lot of RT here, and here RT is actually this plus this because they are in series. If they are in parallel, we are going to what? Use parallel arrangement. As simple as that. Now for this question, the question says, the sum of the current I1 and I2 is dash. It means we are looking for I1 plus I2. What is I1 plus I2? In short, that is the effective current. First, These two are in series. So if you add them together, that's 15. So that 15 and this 10 will be in parallel. How? This is the node. Always look for the node. The battery is between these points. This 10 is also between these points. This 15 is also between these points. So it means the 15, this together, the 10 and this battery, they are all in what? Parallel. So the effect resistance is going to be 15, that's 5 plus 10, 15, in parallel with what? With 10. They will be parallel. This, some of this will be in parallel with this. And I told you, if you have two resistors in parallel, you don't need to solve. You multiply, that's 150. Then you add, that is 25. And then you get the total R to be equals to 6 ohms. Ohm's law, V equals to IR. We are not using E here. Why? No internal resistance. If they didn't mention internal resistance, V is IR straight. What was V? 12. What's I that what we are looking for? What is R6? So that was by 6. I equals to 12 over 6. So I equals to 2 amperes. So it means from this battery, what will come out is going to be what? 2 amperes. So some pass here as I2, then the rest will pass here as I1. They will come together and form another 2. So since you are looking for I1 plus I2, that's straightforward. But I think you have to look for only I2. Let's suppose you are looking for only I2, the current across this one. So the current across this one is just Ohm's law. The current across the 10 ohm resistor, since V is IR, I is V over R. So the current across this 10 ohm resistor is I2 according to this diagram. So I2 equals to the voltage across 10 ohm over the R. And what's voltage? This 10 ohms is in parallel with this what? 12 volts. So the voltage is 12. That was 12 over, we are looking for I2. 12 over what's R is 10. So the current through I2 alone is 1.2 amperes. For these two together, same current to pass through them. Already total current is 2 amperes. So if I do 2 minus 1.2, that's 0.8. It means the current passing these two combinations together is 0.8. So 0.8 is I1, 1.2 is I2, R plus I2 is 2 amperes. But you don't have to do them separately since you can combine them. As simple as that. Now look at this question. An electric cell has internal resistance 2 ohms, that's 1 R. And a current of 0.5 amperes I is found to flow when a resistor of 5 ohms is connected to it. I think this is the simplest question ever. Since they mentioned internal resistance, we are going to use E equals to I to R plus R. So we are given I to be 0.5. The R, external resistance is 5. Internal resistance is 2. So 5 plus 2 is 7. 7 plus 0.5, that's 3.5. So it means the EMF of the cell is 3.5 volts. Very straightforward and simple. Now this question is from 1979:35. We are told to look for the current across this 1 ohm resistor. Find the current across the 1 ohm resistor. Let me call it I1. So for this kind of question, the first thing is to get the effective resistance. Now look at this. These 3 and these 3, they are in series. Because any current comes here, is all passed through this one. So these 2 are in series. These 2 are also in series. So if you combine this and this in series, it turns to what? 6 ohms. This also 6 ohms. So this circuit can be redrawn this way. So now 6, 6. This and this 6, this and this 6. You now notice these 2 are in parallel because they share same node. This one here, this one here. So 6 and 6 in parallel. When you have to resist in parallel, I told you, don't need to use formula, multiply. 6 times 6, 36. 6 plus 6, 12. That is about 12 is what? 3 ohms. So it means we can replace everything here with 3 ohms. Let me draw the diagram again. Now, the circuit is now very simplified. So now you have to be very careful. First thing we did is to combine this to give us this 6. Combine this to give us this 6 because they are in series. Now this one in parallel, we combine these 2, 6 and 6 in parallel, and we got this 3. Now this 12 volts is going to be shared between this and this. Note, our aim is to know the current through the 1 amperes, I1. V is IR, I is V over R. So we have to know current through this 1 ampere, that I1 is going to what? V over R. And what are V1? The voltage across this. The resistance is 1, so you have to know the voltage across this 1 ohm. Remember, they are in series. So remember, voltage divider rule. Shortcuts. So voltage across this 1 ohm, let me call it V1, equals to this 1 itself, 1 over 3 plus 1 times total what? Voltage V. So V1 equals to 1 over 4 times 12. So 4 into 12, 3. It means V1 is what? 3 volts. So coming back here, it means I1 equals to V1 over R, that is 3 volts over what is R? 1 ohms. The answer is still 3, but in this case it's not amperes. So I1 is what? 3 amperes. As simple as that. And this might look long, but if you do it very fast, very simple. 6, 6, 3, voltage divider rule, we are done. Remember, this voltage divider rule is very key. When you have two resistors in series, I explained that in my last class. If you have two resistors in series, R1, R2, and total V is this, then voltage across R1, let me call it V1. V1 equals to R1 over what? R1 plus R2 times V. What about V2? Voltage across R2, V2 equals to, write R2 first, R2 over R1 plus R2 times V. This is faster than using Kirchhoff law. So another thing you can do is you can add this together 4. Get the total what current, you get 3 amperes. It's going to be 3 for total. 3 plus 1 is 4. Then 12 over 4 should give us 3. Oh, there's a mistake here. 4 into 12 is 3. Okay, that's 3 volts. It's correct. Although for this particular case, you might decide not to use voltage divider rule. Why? Since they are in series, it means same current pass through them. So you can combine this together in series. That will be 3 plus 1, that's 4. So even V equals to IR. So if you use V equals to IR directly without using voltage divider rule, V equals to IR. So V is 12. We are looking for I. What is R? 3 plus 1, that is 4. So from there we get our I to what? 3 amperes. It means the current passing is 2 in combined is 3 amperes. Because I see this, it will be 3, 3. Let's take another question. Now for this question, 1983 question 39, the question goes thus. The difference of potential or potential difference between the terminals of a cell is 2.2 volts. Full stop. When a 4 ohm resistor is connected across the terminals of the cell, the potential difference is 2 volts. What is the internal resistance of the cell? I told you, anytime they mention internal resistance, we are going to use this formula. I into R plus R. So, they didn't talk about current at all. But note this. We are given this 2.2 volts is actually the EMF of the cell when there is no condition. But after there is a 4 ohm resistor, that's with R, 4 ohm resistor, the EMF reduced to 2 volts. So this 2 volt is normal EMF again, we call it the terminal voltage. So the terminal voltage is 2 volts. So they ask, what is the internal resistance of the cell? So what are we going to do? We know terminal voltage equals to IR. And it's given to be 2 volts. The R is what? 4 ohms. From here, it means the current equals to 2 over 4. That is what? 0.5 amperes. Next, each cell to supply 2.2, it is supplying what? 2 volts. So it means the loss voltage equals to 2.2 minus 2. The loss voltage equals to 0.2 volts. How do I get that? Recall that EMF equals to terminal voltage plus loss voltage. So this 2 volts is terminal. 2.2 is the what? EMF. When you move this one from this, you get the loss voltage. And according to Ohm's law, the loss voltage equals to I small r. And small r is what we are looking for, which is equals to V over what? I. So what is V? Loss voltage 0.2. What is I? 0.5. So the answer is 2 over 5 or 2 over 5. That will be 0.4 in decimal. A most simplified approach is to use what we call the voltage divider rule. So recall terminal voltage equals to big R into R plus small r times E. So what is VT? 2. What is big R? 4 over 4 plus R times E. And what was E? 2.2. So this 2 equals to, this times will give us 8.8 over 4 plus R. You can multiply, you get what? 2 times 4. 8 plus 2R equals to 8.8. Then 2R equals to 8.8 minus 8 is that 0.8. That was by 2, R is 0.8 over 2. So R is what? 0.4 ohms. Same thing as this. So for this voltage divider rule, if you are given the EMF and terminal voltage and you are not looking for the current, the best is to use this. Or if you know how to play your ways around this, you can also use this. Select your option. The next question is on efficiency of a cell, and during the course of lecture we already said that the efficiency equals to R over R plus R times 100%, as simple as that. So big R is 6, small r is 2 times 100%, and that's 6 over 8 times 100%, and that is 3 over 4 times 100%. So 4 in 100, 25. 25 times 3, that will be 75%. So the efficiency of the cell is 75%. Now for this question, when a resistance R is across the cell, the voltage across the terminals of the cell is reduced to 2/3 of its terminal value. So we know the terminal value is E. 2/3 of its terminal value. So it means the terminal voltage is actually what? 2/3 of the EMF. So then ask, the internal resistance of the cell is. So the terminal voltage is 2/3 of its terminal value when it's not supplying current. It means they are talking about EMF there. So what are we going to use here? So recall the formula that terminal voltage equals to R over R plus R E. So what's our VT from here? 2 over 3 E equals to R into R plus R E. And what happened here? E cancels E. So you can multiply 3 times R, 3R equals to 2 times R, 2R, then 2 times small r, 2 small r. So 3R minus 2R equals to R equals to 2R. Our aim is to get small r. So that was by 2 over 2 over 2. From here it means our small r equals to R over 2 because this will cancel this. So that is the answer. Let's take some question on electrical power and energy. Here we have 2 lamps rated 4 watts and 220 volts each are connected in series. Since they are connected in series, we have to consider their